In this one, we're going to specialize really quickly to this to the case where our harmonic oscillator is both free and undamped. Recall that free means that there is no external force acting on our object. That F external is zero. The purple force here is zero. Okay? And recall that free means that there's no friction force acting on this. So, in other words, both this term and this term are going to be zero in our free and undamped harmonic oscillator. So that makes our equation relatively simple. Yeah, so we're going to look at the free and undamped case. Our equation under these assumptions becomes mx double prime plus kx equals 0. Okay? Now, for really good reason, we're going to divide through by m. And then for a also good reason, we're going to define omega naught to be equal to the square root of k over m. Omega is a Greek letter, and I know it looks like a W there, but it's omega. Yeah, it's a lower. Yeah, that's right. And omega is very often used for angular velocity. Okay, and you're going to see that this plays a role in what we're going to about to do next. Okay. So we're going to define omega naught to be the square root of k over m. And if we do that, then this equation here becomes x double prime plus omega naught squared x equals, equals 0. My bad. Thing I want to say about this is a second order homogeneous linear differential equation with constant coefficients. Yeah, it is. And so we know how to solve these. We just use the characteristic equation, or figure out what the characteristic polynomial is. In this case, that's going to be r squared plus omega naught squared equals 0. How do we solve this? We subtract our omega naught squared from both sides. And then we take the square root of both sides. Now, what is omega naught? Remember, omega naught is this quantity here. Omega naught is square root of k over m. So in particular, this quantity, because k is not 0, is strictly positive. So negative omega naught squared is an honest to goodness negative number. Yeah, it's not 0. It's negative. So of course what we're going to get is a complex conjugate pair of roots looking like r equals plus or minus omega naught I. That complex conjugate pair of roots is going to give rise to a pair of linearly independent solutions. We think of this, remember, as like a plus b plus or minus bi, where a in this case is 0, b in this case is 1, or no, omega naught rather, excuse me. And so our solution, our general solution, is our dependent variables x is x equals c1 times cosine omega naught t plus c2 sine omega naught t. Now, for the purposes of this discussion, rather than using c1 and c2, I'm going to use a and b, because that's going to make things a little bit easier to think about. All right? So a cosine omega naught t and b sine omega naught t. Just relax, okay? T is the independent variable here. A and b are constants, okay? Now, what do these general solutions look like? Maybe the easiest way to understand that is to take a look at, in Desmos, what this looks like. And that's what I've done here for you. Here is what a cosine omega naught t plus b sine omega naught t looks like. Now, if you look at the formulas, if you look carefully there, you'll see that I used x instead of t because the independent variable in Desmos is x. And I used w instead of omega Again, I didn't find any Greek letters there handy. But with Desmos, I'm able to do some experiments, like I'm able to adjust the values of A, B, and omega. All right? And then we can see what happens to the solution. So, first point, look at this red curve here. And please understand this is A cosine omega naught t plus B sine omega naught t. What does it look like to you? It looks like to me a sinusoid. That is to say, a sine curve or a cosine curve, whatever. It looks like the graph of some kind of sine. We call those sinusoids. Okay. Okay, that's interesting. What happens if I mess around with omega? If I adjust the value of omega. So right now omega is 0.7. What happens if I make that omega bigger? Let's try. Hello? Wow, look at that. As I make this omega bigger, right now it's 7.63, we see that the period of this sinusoid decreases. The period gets smaller, right? The wavelength, the amount of time that it takes to do one full wave, one full up and then down and then back, that also gets smaller, right? That's the same thing as the period, right? The frequency increases. The number of oscillations per second increases. Okay. And as we decrease omega, we see the wavelength increasing, the period increasing. Okay? What happens as I adjust A and B? So let me just adjust A. So I'm making A bigger, and you're seeing the amplitude of this oscillation increase. Is the wavelength changing as I change A? No. Do you all see that? The wavelength doesn't seem to be changing, but something interesting is really noticeable here. Do you see that? As I'm tweaking A here around small values, and you can see that, well, it's like the curve is kind of sliding horizontally. Do you see that? What about if I mess around with B? So here I'll make B smaller. You see that horizontal movement again. And then of course as I increase B, we get this increasing amplitude. But yeah, it seems as though if we mess around with A and B, as long as omega is fixed, if we fix omega, it seems like the period of the oscillation doesn't change. But it does seem like the amplitude changes, and so does this interesting phase, this horizontal shift that we sometimes call a phase shift in our sinusoid. All right? So with that in mind, all right, maybe what we can do is rewrite this as some, and maybe I'll say, can we rewrite this as some constant c times cosine of omega naught t? So that omega naught there is to represent the same angular frequency that we saw in our oscillation. The fact that that if we didn't touch omega naught but messed around with A and B, we got the same angular frequency is what inspires me to write this. But then we have this funny phase shift, which I'll represent by doing a minus gamma here. The question is this true? Okay, because we're just kind of postulating that this is true right now. And if it is true, what is gamma and what is C? Well, it turns out we can prove this. So it turns out that yes, indeed, this is true, and I'm going to prove it to you right now. And I'll along the way let you know what C and gamma are. Okay. So how do we proceed? So we're going to use a trig identity, of course, called the angle addition identity. Maybe I'll just call it the angle addition identity. Which says that cosine of A plus B is equal to cosine of A times cosine of B minus sine of A sine of B. Okay. How does one remember this at this stage in your life? Well, at this stage in your life, there are options for doing this. Think about, for example, oh my God, do I really want to do this to you? E to the I A plus B. This is how I remember it. I'm not even kidding. E to the I A plus B. We know by Euler's identity that this is cosine of A plus B plus I sine A plus B, right? On the other hand, this is equal to e to the IA times e to the IB, which is equal to cosine of A plus I sine B, I sine A rather, times cosine of B plus I sine B. So what I'm saying is that the real part of e to the I A plus B is cosine of A plus B. So I need to know what the real part of this thing is. But the real part of this thing is going to be the product of cosine of A and cosine of B. Oh my goodness. Plus I sine A times I sine B. That's the other part that's going to contribute to the real part. But that's negative sine A sine B. You see? And if you know, if you can sort of do that in your head, then you can remember this. So I don't remember this. What I instead remember is Euler's identity, and then I apply Euler's identity to e to the I a sum. Okay. And you can do the same thing with sine of A plus B, by the way. But we're going to pretend that that was a fever dream and it never happened. Or, you know, maybe you take it seriously and use it for the rest of your life. But in particular, one consequence of this angle addition identity, which is very useful in life, is maybe something, is a related inequality for cosine of A minus B. So all I'm going to do to get an identity for cosine of A minus B is replace B by negative B. Remembering that cosine is an even function and sine is an odd function. So if I remember that, then it's pretty clear that cosine of A minus B is cosine of A times cosine of B, right? Cosine of negative B is cosine of B, plus sine A sine B. Very nice. You're wondering what the fuck I'm doing, what I'm doing right now, and I get it, okay? Well, what I'm going to do is now use this identity in the service of simplifying or rewriting this expression right here. Okay? Because what I'm trying to do is figure out what C and gamma are, which will make this true, if it's even true to begin with. What are C and gamma supposed to be? Okay. So what I can do is rewrite this as C times cosine. I can rewrite C cosine omega naught T minus gamma as cosine of C. Well, I'll put a C out here. C times cosine of omega naught T times cosine of gamma. B is playing the role of gamma. Omega naught T is playing the role of A. Plus sine of omega naught t times sine of gamma. Okay? So then I can distribute the c. Because remember, what are we trying to... Don't lose sight of what we're trying to do here. We're trying to make this expression be equal to a cosine omega naught t plus b sine omega naught t. So because we want to write this green thing here as a single sinusoid. And I'm proposing that this sinusoid right here will do the trick. But if it does, we would like to know what c is, and we would like to know what gamma is. And I'm saying we're on our way here. Because look, we've got the cosine omega naught t that we want to see there. And we've got the sine omega naught t that we want to see right there. So then what's playing the role of A and what's playing the role of B? Well, A is going to be C cosine gamma. And B is going to be C sine gamma. So let me note that. So A is going to be C cosine gamma. Oh, that's legit insane. C times cosine gamma. And B is going to be C times sine gamma. Don't you agree? Yeah. Okay, now I still want to know what C is. I want to know what C is. So how can I figure out what C is? Well, I got to get rid of those cosine gamma and that sine gamma in the equation. So how does one do that? Let's use the Pythagorean identity. What? How? Well, I can square both A and B. So A squared is C squared cosine squared gamma. And B squared is C squared sine squared gamma. It's hard to disagree. But then what? Well, then A squared plus B squared is equal to C squared times cosine squared gamma plus sine squared gamma. And by the Pythagorean identity, cosine squared anything plus sine squared anything is 1. So I get rid of the gamma that way. And I'm left with A squared plus B squared equals C squared. Then I can take the square root of both sides, remembering that everything in sight here is C squared is A squared plus B squared. Maybe I'll just leave it like that. Oh, A squared plus B squared is going to be a positive quantity. So C squared, oh, no. Let me not say it like that. C could be negative. Okay, fine. I'll leave this a relationship. So if I want to know what C is, it should be A squared plus C squared should be A squared plus B squared. Okay. Yeah. And then gamma. What can we say about gamma? Well, starting from this line right here, what we can do is divide. Let's do B over A. B over A. Let's look here and look at B over A. B over A is going to be C sine gamma divided by C cosine gamma. The C's cancel, and we're left with tangent of gamma. Okay? So gamma is an angle whose tangent is equal to B over A. So these are nice defining relations for gamma and for C in terms of A and B. So remember how, why did I do all of this work? Because what I wanted to show you is that this ends up being an oscillation. It's an oscillation and we can say something about it, where whose amplitude is this number c, where c is the sum of the squares, where c squared is the sum of the squares of a and b. And furthermore, it's got this phase shift gamma, where gamma is an angle whose tangent is equal to the ratio of b over a. Okay? And that is characterizing this free undamped oscillation. Okay? You can compute omega naught. Don't forget what omega naught is. It's simply the square root of k over m. And now, once you know that, you know it's just going to go up and down, up and down. But if you want to know its amplitude, you compute this c. Okay? All right. In the next one, we'll do some problems involving where we utilize this model to understand some stuff. Okay. See you in the next one.